Hi, my name is Felipe, and I'm a data scientist at Zero Gravity Labs. So we are hiring. We are always hiring, by the way. We will always be hiring. We are interested in people who like to explore and try new stuff. Where shall I start? So I want to talk about a paper that has to do with few shots learning, and I'm going to first get the names right because otherwise, it's not my first language and the names are kind of difficult. So this is called few shot learning through an information retrieval lens by Eleni Triantafilou in U of T and Vector Institute, Richard Semmel in U of T and the Vector Institute, and Rachel Urtasun, then U of T, Vector Institute, and in Uber Advanced Technology Group. So Rachel, Eleni, the first author, that was a really, really cool paper. I found it quite interesting, and Rachel is she's one of the most brilliant data scientists out there. So she has done a lot of, she's like one of those rising stars. So anything that they write is kind of cool. So check it out. So the whole point is I want to talk about something called few shots learning. This comes from the idea that we shouldn't need that much data in order to be able to do stuff. The whole point of deep learning is that if you have a bunch of stuff, you can just find out the underlying probability distribution of that stuff, and then you can get results out of it. But if you look at how we think, we usually don't go that way. You only need to see a handful of examples of something in order to decide that that belongs to a certain category. So the question is, how can we make machines learn just from a couple of examples and get the data out of it, get the information that we want out of it? So a whole field was created, or a branch, that is called few shot learning, and it's shots after all. So the whole point is we want to classify certain data into n different classes where we only have k number of examples per each class. Okay, so we're assuming that k is a small number. Oh, by the way, please interrupt me at any point. This will be a little heavy in the math side, so let me know. So we want to do this classification. So for example, if you have 5 shots, you want to know if they were tequila gin or something like that. Okay, so the strategy that we are going to use, or that they use in the paper, is basically instead of just finding out how similar something is to the class that I'm creating, I'm going to create a ranking to all the possible classes or to all the other possible samples and try to figure out how close I am to the ones that I care about, but I also want to make sure that I'm really far from the ones that I don't care about. And in order to make that into a statement that can be done by deep learning, we'll have to take a road. But before getting there, let's talk about the data sets. So the data sets associated to few shots learning are usually the omniglot that consists in 1,600 characters, about 32 by 32, 50 different alphabets, some of them real, some of them fake, like the Futurama alphabet is there. They take 20 different people and they draw all the characters. So notice that there are only 20 samples per each character. And the other one is you just take the usual ImageNet dataset, you just break it down into smaller chunks and make sure that you just have a few samples per each class. So that's what we're going to use for playing. And let's talk about what has been done before. So here there has been many successful approaches, and I want to talk about a couple of them that are quite ingenious. So the first one is a little natural. So you basically are going to use an attention mechanism, you have the classes and you have some attention function that is going to decide what is the probability that belongs to a class. So it's basically, you have an attention that is just comparing the similarity between your input data and the current image. And then you are just going to combine this with a softmax in order to create just a probabilistic distribution on the different classes. Now, this is really nice, it's really simple, really naive. If you try it out of the box, it won't work. This will give you relatively bad results. The reason is because you really need to create a nice attention mechanism for this to be well behaved. And the kind of attention mechanisms that you can just use 2 different neural networks, 2 common nets, in order to do the embedding for, say, this input, and you may use another one or the same common net to do the second position. And then you just can use something like the cosine similarity to compare how close this class is to this class. And after that, you can use on like the softmax function in order to decide which class this does it belong to. Does that make sense? Am I going too fast? Okay, good. So they find out that in this way, the on-Miglo data set, just with one image at a time, with one sample, they were able to get an accuracy of 98%. This is kind of really surprising. You only gave me one sample, and just with one sample, I was able to determine how likely you will be to belong to that class. But if you remember, the Omiglo data set was really, really unique, right? You have like only some lines drawn, like it's kind of really a little artificial. So they also compare what happens in the ImageNet. And if you only have one image and you want to classify into 5 different classes, you get an accuracy of 46%. That's still quite good, taking into account like the randomness will give you like 20%, but just out of one image, you were able like almost half of the times to get it right. So yes?
So what did they use for X and XI? So you said they used a deep neural network?
Yeah, so you can use anything that you want.
They trained on some images, right?
No, they train it on the spot. So basically they have the network, they can have one network for the first input, for the first component, for this one, and you have another network for this one that basically is going to create vector embeddeds into the same dimensional vector space if you want, and then you use cosine similarity to compare, but the networks are going to be trained just with this number of samples.
One shot, I mean...
it's quite surprising.
Are you sure?
Are you sure that they're doing that? Because I would think, yeah, like that.
It's really surprising.
Like, yeah.
I know. But I mean, like, if you compare to the standards of ImageNet, come on, like this is really far from the standards that you have. Like in ImageNet, nowadays, Wasim, do you know what is the accuracy for ImageNet right now?
I think there is top 1 and there is top 5. Top 5 is like 97 point something, almost 98 now. But for 1, I think it's around 75%.
So, and we'll see. Like this is really amazing. But the whole point is, this is telling you like there's actual information there that you can capture just with one sample. The question is like, how do you go about these samples? How do you go about training? And you are right in being skeptical. They actually use a really nice amount of tricks for this attention function, because if you use this naive approach, it just doesn't work that well. So they have, in order to create this, they use a really nice way of embedding. And they don't embed just that sample, they also embed like some family of samples, like some set associated to it. And they also do a really clever training just by sampling and some other stuff that I didn't understand, because this is not the paper that I read. But like, this is what they reported. It's pretty neat, but it's not the only one. This one was probably one that got me fascinated. I don't understand all the details, but I thought it was extremely cool. Like, it seems that one of the main problems that we have when training neural networks is that we don't know how to update the learning rate. This is difficult in general. That's why we have a scheduled learning. That's why we have all this bunch of stuff. But what if you actually try to make the scheduled learning to be something that you actually learn? And you try to learn it just by using some recurrent neural network. And that will be amazing, right? You are just doing a meta learning. You are learning how to actually update the learning rate in order that you are able to go to the minimum much faster or more efficiently. That's amazing. And these guys did just that. And the key point is that they noticed that when you are doing gradient descent, the update for the cell state in the LSTM is when you are doing the update for the cell state in the LSTM is exactly the same as doing gradient descent. The equations are almost identical. So they take that advantage and they find out that they can learn the learning rates by using LSTMs, and then they use that in order to do a training of this network. This is another thing that I don't know all the details. I only know that that's what they did in the bottom. And it's fascinating, but they do report something that is crucial, and it's that it's really delicate. They spend a lot of time optimizing this thing. Like, it seems that there is, like, if you change a little bit somewhere, just it breaks down. So like, an interesting idea, they report results for the ImageNet of 43% and 60% that are equivalent to the matching ones. So that's pretty cool. But these guys have a completely different approach. and it's a wonderful approach. So let's try to change the setup. And this is the part where I need to begin introducing a lot of concepts. So as I'm going to be introducing stuff, I'll try to go slow, yes?
So just before that, a clarification question. When you say one-shot learning, if we go back a couple slides, maybe get to, yeah. So when you say one sample, do you mean one sample from each category?
Yes, yes, one sample per each class. Yeah.
How many classes?
In this case, 5 or 10. You have almost no data.
So 10 examples.
Yep.
And you're starting from like just initial like uniformly randomized data, like the data.
Yeah, but like you should.
Like fine tuning going on, so retraining or something.
I'm pretty sure they did some fine tuning, but like you should be aware that this is just a problem. That doesn't mean that they only use those 10 images. They could solve. They can use this. They attack the same problem by just using. Let's take another 5 random classes and take one sample per each class, and I still want to solve the same problem. Does that make sense? It's not that you just have 10 images. You are just applying the same network in many of these problems. But let's talk about this one that is much cooler, okay? So the goal. So here is my goal. So I want to find a way of classifying the inputs in such a way, but I want not only just to obtain what is like, when I give an input, I don't want just to obtain what is the most similar class to this input. I want to rank every single possibility for all the other inputs. I want to say like, yeah, this was really similar to the one that you are sending me. The second image was also really similar, and so on. I want to have a structure. I want to have an output that is a ranking of all the inputs that you have compared to the one that I'm giving. So I'm going from, like usually when you think about classification, you usually obtain a label. No, here I don't want to have a label. I want to have a ranking. I want to rank everything else. So how are we going to do that? It's difficult. Like, how do you measure what ranking is better than another ranking? How do you deal with something like that? So we need to build a formalism in order to work with that. And the way that we do it, well, so let's work it out. So you have a batch. You have endpoints in a batch. Each of them belonging to some classes. They may be different. They may be equal. Well, some of them may be equal. The point is that you have the classes. So for example, we have a batch. We have 5 points, and 2 of them are in the red class, 1 in the blue class, and 2 in the green class. And for each class, I want to create a set that is the relevant points to that input. And the relevant points are basically all the points that have the same class. It's nothing particularly difficult. So the relevant points to x1 is x1 and x5 because they are in the same class. The relevant points for x3 is just x3, then nothing else was relevant. And the relevant points for x2 and x4 was x2 and x4. Okay, so far so good, right? Sorry, I have the tendency to speak really fast.
Relevant points are points which are of the same
class. Yeah, and just basically like equivalent classes. Yeah.
Can you repeat what you mentioned about the rank again?
So the whole point, we'll see it in a second actually.
Okay.
So now that I know which ones are relevant, I want to begin. Let's keep the information here and let's actually find out what this means. So my output will be the predicted ranking based on the similarity of xi and xj. More precisely, this will be the vector such that in the j component will be the j thing that I predict that is more similar to xi. Does that make sense? So basically I have all my things and I said like, oh, well, let's do it here. So for example, this could be an output. And this is basically saying that under the current state of the system, x2 is really similar to x2. Well, that makes sense, right? The most similar thing to something is itself. Then it's saying x1 is similar to x2. This is not that good because x4 is more similar because it is in the same class. Then he's saying like the third most similar under the current state is x4. This is good. The fourth more similar is x5, and the fifth more similar is x3. So this is the ranking. It's basically saying this is the most similar, this is the second most similar, the third more similar, and so on. And we want to make sure that this ranking is as good as possible. Does that answer your question?
So why is x1 more similar to x2 than x4?
Because this is not trained yet. This is like you start with a random thing, and this is what we want to optimize. We want to create a network such that at the end X4 will be on top. So, but we still don't have a way of quantifying this. We still need to quantify it in some way. So we need more data. So let's keep this thing. Yeah?
So, I mean, usually don't you get this and don't you get some probabilities and CNNs, the probability that this belongs to this class or some probability?
You could do it that way, and that will be a way of comparing them. But that doesn't mean that those probabilities may still give you something like this. Like so far it's just the ranking. I haven't tell you how to get it, but like that's one way. That's perfectly fine. But they will use another technique. So what are they going to do? We still need to weigh a way of measuring how good this ranking is, and they use something called precision. So the precision at the point j of the ranking given by xi is the ratio on how many points have I seen how many points relevance have I seen over the total number of points that I have seen up to that point. Okay, so sounds kind of tricky, so let's actually go through the example. So for example, here the precision at the point 0 for x2, the precision at 0 of x2 is 1/1. Why? Because I have only seen 1 point. I have only seen 1 point, and it was correct. It was in the right class. The precision at 1 of x2 is 1/2, because so far I have seen 2 things. I have seen these 2 things, but only the first one was correct. The precision at 2 for x2 is 2/3. I have seen 3 things, 1, 2, 3, and these 2 were correct, and so on. So this is telling you, as you move down in your ranking, how good your ranking was. Now notice something. Precision, every time that precision is 1 is that it's accurate. The first time that it makes a mistake, it goes below 1. Is that how it goes? The first time that it goes to a different class, it goes to below 1 and it never recovers. So that's precision, okay, but we still need more. So let's keep the precisions and let's do more. Let's take the average of those precisions. So, but I'm not going to take the average over every single precision. I'm going to take the average over the precision of the classes that are relevant to the point that I'm sending. And this is important, because basically I'm looking at the points that belong to the same class, and I'm only looking at the precisions over those points, and then I'm taking the average over those. Why? Because then I obtain this quantity, and this quantity, notice that here the only relevance were the first one and the second one. This one and this one were the only relevance. So I only add up the precision of those 2, and I take the average. This is important because, okay, quiz time. This is one if and only if what?
The ranking is exactly right.
If the ranking is right, at least for the class relevant. So this is a measure that is one if and only if you have ranked correctly all the classes that are relevant to you. Otherwise, it will never be 1. So that's pretty good. We have something that tells me 1, I'm good. Less than 1, there was some mistake somewhere. But okay, this was only for the input x2. It will be nice to have it for every single input. So you can repeat. So let's keep the result there. We need to repeat that procedure for every single input, and then just take the average over the batch size. And that is called, well, you just do it this way, and that's called the mean average precision. And in this case, it's kind of lucky that English has 2 words for mean, because then you can say mean precision will be kind of, or average precision, yeah. So, okay. Anyway, so now that we have that, let's talk a little bit like why is this kind of a tricky thing to deal with. So, oh, I should have mentioned other things before, but like, I can mention it now. So, why should we care about this problem? I'm just going to make a small parenthesis because I was supposed to say that at the beginning. Why should we care about this problem?
What problem?
Of being able to classify things with a small amount of data.
Because we don't have a lot of label data.
So we don't have a lot of label data, but so let's go from helping humankind to helping ourselves. So if we have, like in many cases, like for example, really strange cases of diseases, there's not a lot of data, and being able to distinguish between really different cases of strange diseases is kind of difficult. But if you have a way of classifying these things, then it will be kind of helpful. So for rare kind of things, it's helpful to have that kind of classification. That's one case. Let's get closer. In vision, like for example, if you have classifying between what is a bird and what is not a bird is relatively easy, I guess, if you have enough samples. But classifying between different kinds of birds, it gets more challenging because there are not that many pictures of like some random birds, right? That's a difficult problem. But now let's go to the part the industry part. Most of our companies rely heavily in that we have tons of data in order to produce the results that we have. If suddenly someone comes and tells you, look, you don't need that much data in order to produce good results, then a lot of the value of our companies is screwed. So being aware that these techniques are being developed and what is the reach of these technologies is kind of important. That's one of the reasons that we're exploring this at Zero Gravity Labs, because we need to make sure that we still have the value that comes with a lot of data. Okay, that being said, that was the part that only cared about us. Let's talk about what we care in real life. So in real life, if I tell you that when you look at the tables that you get in all these things, you're always reporting accuracy, right? You're not reporting like a cross entropy. You're not reporting binary cross entropy. You're just reporting accuracy. Accuracy is the loss function that you care about. You don't care about like, I got it almost right. No, you don't care about almost right. You care about if you got it right or not. But if you try to compute accuracy, let's say in a binary classifier, how do you do gradient descent for this kind of stuff? So suppose that your goal, your loss function is accuracy. How do you do gradient descent on that?
Well, you define a surrogate.
Yes, exactly. You define a surrogate. Yeah, hopefully. But you need something else, right? So in this sense, the mean average precision also needs a surrogate. But we actually need a whole new system in order to deal with that surrogate. So the question is, how do we find that whole system? What is the things that we need to replace? So most of you are data scientists, so I hope that you're okay with what I'm going to show, or you should be okay at least. Support vector machines, right? All of you may have seen it at some point, so we have some input. So we're going to build something called structural support vector machines. And the way that I'm going to present it, this is actually the main component, is I'm going to remind you how support vector machines work briefly, and we are going to build on top of it, okay? So in support vector machines, you have something that you want to classify in two different inputs, right? And you're basically building a hyperplane that is going to separate the points in the best way, meaning that you have the largest margin. That's nice, that's how the model works. And if you remember the equations, this is what I love. I love math, I'm a mathematician. So this is beautiful. Like basically they change the problem into a mathematical equation. So if you have seen this before, you may notice that this is a slightly different how it usually is presented. I promise you it's equivalent. This is just like I put in a 2 here that you can carry inside the W. But this is the soft margin support vector machine. It's basically the support vector machines that allows for errors. And this is telling you this is the boundary condition that is important. So this is basically telling you what is the size of the margin. This is telling you how much error you are allowing. This is basically the classes that you have of plus minus 1, basically trying to figure out if you are well placed in the right size of the plane. So this is how support vector machines goes, but let's dive in a little deeper in this. So there is a scoring function. There is a scoring that is basically this part is telling you how well are you classifying. Every time that you put a point, it's telling you not only if it is in the right side, but it's telling you how good you were in that side. You're assigning a score to that input. So it's telling you, good, you did a good job. But we also have something that I found more interesting. We have a loss function that is basically telling you if you got it right or wrong. And for the mathematical inclined, this is actually really similar to a distance function in a discrete space. And it will actually behave like that in general. We will have that the loss function in general it will be a discrete space, and you want to have some distance measure that is well behaved. So we have these two components here, and this one corresponds to this one that is basically saying if you got it right or wrong. Once you have those things, you have something pretty cool, is that you can rewrite this equation. But now we want to rewrite it. We don't want the output to be plus minus 1. We want some vector, some structure. So we still want to minimize over the same function. We will need a loss function that works like a distance. We need a scoring function that tells you how good you did with that sample. And this equation is exactly the same equation that we had before, where I replace for the scoring functions and the loss function. Something that is important here is that you will need those conditions for everything in the output space. So the more classes you are trying to classify, the more equations you will have here. In general, dealing with these kind of problems will be extremely hard, but there are tricks, and that's a little bit what I'm going to talk about. So the scoring functions, the scoring functions, usually you want something that is linear in the W's. In the X and Y doesn't matter that much, but it should be linear in the W's. So the so this becomes a convex problem, and basically you can apply subgradient descent techniques. But if you use something else, there's still a way around, but it becomes much harder.
Is this the kernel trick?
No, but it's not exactly the same, because the kernel trick is applied later in the training when you are doing, like, if for example, it depends how you are solving it, but like if you are doing the kernel trick using the Lagrange dual, then that's where the kernel begins showing up in order to do the minimization. So the kernel trick, as I remember it, for support vector machines, you need to pass to the dual problem, then you can have some sort of kernel, like the kernel is carried there, and then you just compute it there because it's simpler. But that's my memory, like it's been a while.
It's kind of like variational based, basically. Your scoring function is your kind of posterior, and your real loss is that one you're trying to kind of.
That sounds reasonable to me.
Yeah.
Yeah, that sounds reasonable to me.
But then how is that variation?
No, there's no variation. You don't really need variation when you solve the problem. You just create like as many discrete kind of strings. Yeah. Yeah.
Well, so the point is that this is the setup. And the good thing is that once we have this setup, really nice setup, let me write it again. This seems that there is a theorem that is in the paper or in one of the references that says that finding this minimum gives an upper bound to the average loss. So finding that minimum of that problem actually has a way of giving an upper bound. So if you decrease that upper bound, you decrease the average loss. And that's exactly what you want. So that's why it's a surrogate. You are not really decreasing the loss directly. You are decreasing something that forces the loss to decrease. And the way that is updated, this comes in updating 2 steps. Basically, the training method is, again, notice that this is a discrete space and it has only finite many samples. So this is something that you can check just by plugging in all the possibilities. So you just compute the Rmax of this thing, and then you use that Y parameter that you obtain there in order to update your weights. So it's a 2-step process, but like, again, this is relatively easy. This is trivial. So this is the interesting part. And if F is linear, this is really easy to compute as well. So this is pretty good. Now, yes?
So you have Y sub I and you have Y there, right? In the top right corner.
Top right corner. Here?
No, well, yes, there too.
Oh.
So what does the I stand for, and what does the only Y stand for? Which one would be?
Yeah, I guess there is there a problem with the order of these things? So I fix first an I, and then I need, basically this is going over all pairs. I could have written I and J, YI and YJ, and go over all possible I and J's that are distinct.
Okay, so the other Y is actually YJ. Or?
It doesn't matter, it just goes over all the space. And this is saying I also go over all the spaces. Terrible notation that I copy from the paper. But like basically it says like you are just going over all the outputs, all the combinations of 2 outputs of the space. So with this updating, like everything works well. And this is just one of the techniques. And before I keep moving, so this is just one of the techniques, and this is a general technique. Again, this works relatively well when this function is kind of linear in the W's. Otherwise, it becomes a little trickier, but still this kind of updates work, or something similar to them work. The difference is like how you have to do it. Like this one will work directly if it is linear. Otherwise, you actually, like to solve this problem, you need to go to the Lagrange dual and solve the dual problem, which is just a computational technique in order to solve a constraint problem into another constraint problem that is relatively easy to solve. Okay, so let's talk about what are our scoring functions and our loss functions for the thing that we have. Our loss function should be something similar to the mean average precision, right? I thought I messed up the order. Okay, no, mean average precision, it should be something like that. But the scoring function should also be really interesting. And for this scoring function, this is just a normalizing, so don't worry too much about this part. The interesting part happens here. And what happens here? Well, this part here is basically a cosine similarity of embeddings of your choice for the images that you have. So you can use I don't know, let's say something really silly. What is PCA for the images? To see if that's your vector embedding, and then you use cosine similarity. That may not give you much. Or you can use a really long convolutional neural network, and that may give you a better vector embedding. The whole point is that you are taking the cosine similarity of your embedding. In their paper, they use just a neural network, a COMNet, I think 5-layer or something like that, I don't remember. So basically this is comparing how close xi is to xk. This here is comparing how close xi is to xj. This difference is saying they are ranked in the right order or they are not. So we need a penalty that says, like, if they're ranked in the right order, be 1. If they're ranked in the wrong order, it's -1, so you get a penalty. So with that information, you get a function that basically assigns a better score if you're ranking well than if you're ranking wrong. And therefore, like, this is great. This is sort of what we want. We have a scoring function that basically tells you how good you are ranking. And that's what this function does. And that's the scoring function. This is just normalizing. And yeah, and that was basically the embedding. And our loss function, we want the loss function. I mean, we don't want to say that 1 is a perfect loss function, right? We want to say 0. So we just switch. We just go 1 minus mean average precision. So this will be 0 if and only if I have ranked perfectly. Make sense? That's basically like the main components of the paper. Well, half of the main components of the paper. That's what I tell you, the paper is really amazing. They also develop another technique called direct loss minimization, where they don't go to the surrogate, they just find a way using a theorem in order to train directly from the loss function. But they report about the same. The matching networks, they beat it by a little bit. And there was the other one that I don't remember which one of these it is. But they beat that one, but they also create something here that is new, that is basically something that they call retrieval, that is how good were you at ranking. And there isn't something like that before, so this is the first time that a score like this shows up. This is pretty good. They basically do like about as well as everybody else, but the technique and the approach is completely different, and that is really important. And for the mini image net, they also do slightly better than everybody else. So it's also an improvement. Now, let me make 2 comments. The first one is that they really use another technique, and in order to use that technique, they have to go over another set of theory, another kind of paper that is relatively similar to what I discussed here, but they really need to go slightly deeper into how to compute the gradients for this thing. That's one thing. And the other thing, they piggyback, computing the mean average precision is like, it can be really, like, if you just do it with whatever comes to your mind, it will be like really inefficient. So there is an algorithm that they piggyback on, and it's another algorithm that shows that there is dynamical programming in order to compute the mean average precision that is efficient enough. So for the results. And I think that's it. Thank you, guys.